Hello everyone, and welcome to this last part. This is the third part of the notes for section 3.1 where we're talking about quadratic equations and quadratic functions in particular. I want to take a look at this example number 3 because we're going to be responsible in this example for basically coming up with a quadratic function and then doing something with that. In particular, we're trying to maximize, which is the term that we would want to use when it says find the largest area. This is a problem having to do with this kind of an idea, optimization. And in particular, we're trying to find a way to maximize a function. And so what it's talking about, it says a farmer with 2,000 meters of fencing wants to enclose a rectangular plot that borders on a river. And so we've got some type of a river along here, and we're assuming that the edge of the river is very straight. And then this farmer is going to come in here and he wants to build a fence. And so he has 2,000 meters of fence that he can use, and he wants to enclose a rectangular plot. So basically you can imagine that he needs to use some of the fence perpendicular to the river. He needs to use some more fence in a parallel kind of a fashion, and then he needs to use the fence over here. Now, since it's a rectangle, we know that basically these two sides need to be the same length, and so we could give those a mark from geometry, like they need to be the same length, and then these two sides over here, they need to be the same length, this side over here, and so we could give a mark like that. And then, as is customary with this algebra that we're doing, we're trying to find the largest area that's possible over here, and since we don't know the lengths of these three sides, because of course along the river it says there's no fence going along the river, so we have three sides of a fence, two of the sides are the same length, and then the other side is a different length. So these two sides that are the same, we could call them both x, and then the side that's different maybe we can call y. And so here we want to come up with an equation for the area, and of course since this one's a rectangle, it just goes the length times the width. And in this case, it doesn't matter if you use x and y or if you use maybe L and W for length and width. It really is going to make no difference. I just chose x and y because we're used to using these all the time. And so this equation's very good, but there's not a lot that we can do with it because we're trying to maximize this thing, trying to maximize this area, and there's not a way for us, at least with the tools that we have, to be able to graph something that has two variables. See, if we wanted to come in here and call this, for example, a function area of, like a of xy, where basically x and y are variables, it's possible to graph it. You need a three-dimensional graph, and that's not what we're into, so we need to figure out a way to turn this into just one variable. So we need to have only one variable. And of course there's a way that we can do it because it gives us some other information over here. We know that he has altogether, this farmer, 2,000 meters of fencing. And so these three sides, the side that goes x, and then also this side that goes y, so if we add that side and then we come and we add this other side, we add up all the lengths of the fence, we know that he has overall 2,000 meters of fence. And so we could, for example, solve for y in terms of x. Maybe I'll rewrite this one. We can just combine this like term, these two x's. It will go y plus 2x equals 2,000. And so then y is going to be 2,000 minus 2x. And now we could actually just plug this one in to the y value over here for the area. And what we would end up with, I'm going to write it over here, is that the area is going to be x times, which in this case that's the width, times the length, which we found an expression for the length in terms of x, which is 2,000 minus 2x. And so we have actually now another equation that this one would be a quadratic equation, because if we come and we distribute this x, then it will go 2,000x minus 2x squared. And so now this function, it does not have two variables, it only has one. And our task is to find out what is the largest area. So what is the largest that this value, that a value, can be whenever we consider all the different values that we can plug in for x. And so I'm going to get a little bit more room right here. And I want to think about what kind of situation we're dealing with over here. For one, we can graph this function and see what the graph looks like. And one of the ways that we could graph this, I think it would be very convenient just to factor this thing the way that we had it, and we can find the zeros. And so what if we actually need this function over here the way that we had it before, which was x times 2000 minus 2x. And then both of these terms are divisible by 2, so we can actually take out the 2 as well. And we will end up with our function a of x is going to be 2x and then times 1000 minus x. And so we can tell from this form that one of the zeros, for example, if we say a of x equals 0, and we find the solutions for this one, that 2x times 1000 minus x equals 0, we will get that x equals 0 is a solution, and also based on this term we will get that x equals 1000 is a solution. And so we can plot those zeros. We have 1 at 0 over here, and then we have 1 at 1000. And then the vertex should be halfway between the two zeros, so the vertex is over here halfway between 0 and 1000, of course, is 500. And so we have that the vertex is at 500. And this one, of course, taking a look at the way we wrote the form whenever we distributed it, there is this negative in front of the x squared term, and so that means that this parabola should be facing down. And so the vertex will be somewhere up here, and the parabola is facing down in this way. And so it should be perfectly symmetrical. Of course, my drawing is not perfect. But anyways, the vertex here obviously is going to be where the maximum is. And if I drew it maybe a little bit better, I will try to make this vertex seem a little bit more clear. The vertex for sure should be the maximum for this graph. And it would be possible to find it if we just plug in 500, because we know that that's where the x coordinate is. Then this is going to be the point where the area with an x value of 500 is equal to what? What is this area going to be? We need to plug in 500 for x, and then we'll be able to calculate the area. And so 2000 times 500, there are 5 zeros, and then 2 times 5 is another 10, so 10 with 5 zeros behind it. I think this is going to be a pretty big fence, don't you think? At least a pretty big area. That should be correct, 100,000. Actually, no, that's 1 million, that's very good. And then we have minus 2 times of 500 squared, where 500 squared is 25 with 4 zeros. So that's 1 million minus, of course, this is 250,000, we're going times 2, so minus 500,000. And this is 500,000 as our answer. 500,000, and this fence, it should have been in feet, so this is square feet. The fence will be 500,000 square feet. And so that's the maximum area that's possible. We are dealing with a situation, we can imagine what that fence looks like. It has the fence that's coming this way has a length of 500 feet. And since he has 2,000 total, we're using up 1,000 of it. That leaves 1,000 feet over here to make this side of the fence. And so if we construct our fence exactly like this, this is the largest area that's possible to enclose. And so you can imagine that, you can make all different kinds of sizes of fence. We can make it taller this way and shorter this way, but it's going to have a smaller area. That's what we're seeing here. If we choose all these different x values, we always end up with a smaller area than if we choose the x to be 500. So thank you guys for watching this video. That does it for 3.1, and I'll catch you guys in the next video.